So in this video we're going to look at sketching log functions. Now, just like with sketching exponentials, the key to this skill is knowing what the base function looks like and knowing how the transformations work, or transformations work in general. So what we're going to do is we're going to draw a little set of axes here, and we're going to go y and x. Now I'm just going to start by drawing an exponential, which might sound weird at the moment, or not a very good exponential, but it'll do. So this is a exponential. Now, a log function, if you cut a 45-degree line across this set of axes, a log function is the 45-degree mirror image of an exponential. So it's not mirrored on the x or the y-axis, it's mirrored across that 45-degree line, that y equals x line. So, thinking back to some key features of an exponential, we normally have a y-intercept at 0, 1. We already have a point here at 1 and e. If you need to be reminded of those points, you can simply go back to the exponential video. Now, why am I mentioning the points of an exponential in a log video? Well, if this is a y-intercept, then when you mirror that, and you mirror that across that dashed yellow line, then your y-intercept becomes your x-intercept. And that also means that instead of being at 1, 0, 1, we're going to be at 1 and 0. The same thing is going to happen here for this random single point. Instead of being at 1 and e, then we will be at e and 1. The other thing that changes is an exponential. Normally, we'll just have an asymptote. I'm just going to quickly do this in highlighter and then rub it out. We would normally have an asymptote across here at y equals 0. Now, because we are a log and that's all been flipped across that dotted line, what we now have instead is a vertical asymptote. So we would have vertical asymptote at x equals 0. So the exponential would normally have a horizontal asymptote at y equals 0, but it gives this perfect 45-degree mirror image of an exponential. So let's get into graphing. Alright, I'll just slide this down a little bit. I might run out of room. We are going to graph y equals, I'm not going to write log e, I'm going to write ln, x take 2. So this is a h transformation. That means h is -2, which means in this case the whole graph has been moved or translated to the right 2 units. So what does that change? It hasn't stretched my graph. It hasn't changed whether my graph is any skinnier or any wider, but what it does mean, and I'm just going to draw my axes manually here, what it does mean, instead of having a asymptote at y equals 0, I'm going to have an asymptote here. Oops, not at y equals 0, x equals 0. So now I'm going to have an asymptote at x equals 2. So I'm going to have vertical asymptote at x equals 2. And what that means is every one of these points has been shifted across 2 units. So instead of being at 1 and 0, I'm going to be at 3 and 0. Instead of being over here at e and 1, I'm now 2 units more to the right, which is at 2 plus e and 1. Of course, if I was using decimals, I would put a decimal value in there for that 2 plus e. Question B. We're now looking at y equals ln x plus 1 plus 2. So we've got a couple things going on here. We said before that the -2 means that we were going across 2 units. Now we've got plus 1 and we've got plus 2. Now they're going to do different things. One of these is a h transformation, just like this one was, and now we have a k transformation. So the -1 means I'm going to go left 1 unit, and then this +2 means I'm going to go up 2 units. So our transformations for our h are kind of working back to front, and our k is doing exactly as it says, +2, moving up 2 units. So again, I'm not stretching or squashing this graph, I'm just sliding it left or right. So here we go. I'm going to do my vertical asymptote first. It's one of my major key features. So in this case, I'm going to move it across here, and I'm going to say verti asymptote at x equals -1. Now I'm going to still have to put in some points, so I'm just going to draw this first, and then we're going to work out where they are. Now, two things are happening. Let's think about where our x-intercept was before. It was normally at 1 and 0. However, I have gone, I'm going to put this coordinate over here, I've gone 1 unit to the left, so I should be at 0 instead of 1, and I have gone 2 units up, so I should be at 2. Now, hold on a second. I have started trying to label an x-intercept, and I somehow have a y-intercept? Well, if that's the case, I should be putting my y-intercept where it belongs, and I should be putting it up here, 0 and 2. Now, how do we know that that is actually the case? Well, let's go and substitute into my log equation. ln of 0 plus 1 plus 2 is ln of 1 plus 2. ln of 1 is 0 plus 2, which is just 2. So yeah, that checks out. If I substitute in 0 into my equation, I do get 2. So our transformation is working. The next one is we need another point. So we started on the left trying to work out where this x-intercept is, and we somehow found out our y-intercept. Well, let's flip the script here a little bit. We still need to find the x-intercept, because there still is one. Well, another way that we can find the x-intercept, we know the x-intercept is where y is equal to 0. So we've got this equation, y equals ln of x plus 1 plus 2, but we want to know where is this x plus 1 plus 2 equal to 0. Well, good question, right? All we have to do is rearrange this by using exponentials. Now, in a previous exponential video, we solved them by using logs. Well, if we want to solve logs, we can use exponentials. They are inverses of one another. So ln of x plus 1 equals -2. Now, if I want to get that x outside of that log, I'm just going to go across here a little bit. What that means I can do is I can go e to the power of ln. Now, this e to the power of ln x plus 1 is going to equal e to the power of -2. And what's actually going to happen here is this e to the ln is just going to cancel out. So instead, it's not actually going to be up here in a power. It's just going to be x plus 1 equals e to the -2. Now, as soon as we've got our x outside from our log, it's a nice easy solve. E to the -2, take 1. Now, that would be my exact value solution. If we wanted to work out what this is as a decimal, we very much could. We could just simply put that into our calculator. Now, at the moment, I'm just going to leave it as an exact value, and I'm going to write x-intercept here is at e to the -2, take 1, and 0. That is my x-intercept. I've got an x-intercept, a y-intercept, and an asymptote. They're getting a bit trickier. Alright, let's go to C. C, 1/4 ln of 2x. 1/4 ln of 2x. So before we had a h and a k, now we have an a and a b. Now one thing we can do is we can think about our asymptote first and then think about whether or how much our graph is being squished or stretched. Now why do I say that? Well, an asymptote is only ever going to be dictated by the h value, how much the whole graph has been slid left or right. It absolutely does not matter what is happening here with this a and b value. So what that means is I can put any value into this, but because there's no h transformation happening, it means that my asymptote hasn't changed at all. So if I was to look at this immediately, what that means is my asymptote is going to be here at x equals 0. So I'm going to have vertical asymptote at x equals 0. Now, that doesn't mean our other points are in the same spot. So I'm going to be doing something like that still. Let's have a look at my graph. Are any of those transformations negative? Well, that's not a negative in here, and that's not a negative in here. So there's been no reflections, so my shape of my graph is still correct. That's good. The difference is this location still the same? Well, let's have a check. This is where x is equal to something, where y is equal to 0. So what we can do is make this whole equation equal to 0 and see what we get out of it. So y equals 1/4 ln of 2x. So where this whole equation equals 0. Now of course, where this equals 0 is where ln of 2x equals 0. We can think null factor law if you want. Again, if I want to solve for what x is, I need to be using exponentials. So I'm going to do e to the power of on both sides. E to the ln is going to end up cancelling out and just leave us with a 2x is equal to e to the 0. And 2x is just equal to 1, because e to the 0 becomes 1, which means x is equal to a half. So that means, yes, things have changed a little bit. My x-intercept is now at a half and 0. The other one that we now need to look at is another point somewhere. Another point somewhere. Now, I could put in a value of 1, x equals 1. However, if we look back over at this example here, we saw that it was quite easy to solve. I'm just going to highlight a certain section. It was quite easy for us to solve this log because ln of 1 is always equal to 0. That's a nice easy one. So if I ever want to solve a log here manually, I want to be able to do ln of 1. So looking at my equation, I can't just do ln of 1 if I sub in x as 1, but have a think. If I was to sub in x equals a half into this equation, so if I was to just pick a point here and go x is a half, y is equal to something, well, if I was to substitute in x is equal to a half, the reason that would work is because that is going to ask me and simplify down to what is ln of 1. Well, we know what ln of 1 is. ln of 1 is just 0. So a quarter times 0. So 0? Well, that simplified way too easily. But how is that possible? Well, we just worked out what it is when x is a half. That was just over here. So, that's not going to work. I can't choose that point. It would be nice if I could choose that point. That's usually a nice point that we want to choose. But we can never pick a point where the log becomes 0 in this case, right? We can only pick that when there's a plus k value on the end. So instead of that, sadly, let's pick another point. Maybe we do have to pick a point that maybe isn't quite nice. So let's pick that point of x equals 1 and see what happens. All right, so we now have y equals 1/4 ln 2 times 1, which is, sorry, I said 1/4 and wrote 1/2, which is 1/4 ln of 2. Now, that's not really that nice of a number, so I guess that's just what we write, 1/4 ln 2. And you can see why before we would have wanted to make our log equal to 1. It would have made things a lot nicer to work with. But sadly, we'd already used up where ln of 1 is. Alright, last example, y equals negative ln of negative x. Here we go. Y equals negative ln negative x. Now, this is the last example, and somehow it is the most simple example. It looks the trickiest because of all the negatives, but let's do them slowly. This is a basic log. Let's think about, in yellow now, this negative. A negative like that flips things across the y-axis. Now, I'm going to think about the next log. This negative is going to flip things again across the y-axis. Across the x-axis. So, getting rid of everything we just had. Our normal one, like we said. I then flipped it across the y-axis, which is what we see here. And we then flipped it across the x-axis, which is what we saw here. So, let's get rid of all this. What we're going to have is a vertical asymptote still. We still end up with a vertical asymptote here at x equals 0, because again, no h transformation, vertical asymptote. And we now need to think about what these values are equal to. So normally we'd be sitting over here at a point like this of 1 and 0. However, I'm sitting over here, so it's making me think I need to look for a point of like -1 and see what happens. Well, again, we've got the function here. We can just test it. So let's do exactly that. I'm going to go y equals negative ln of negative 1. That's going to be a bit confusing. Negative ln of negative 1 is positive 1. And just like before, we know that ln of 1 is 0, so we'll be at -0, which is not a thing, so just 0. So yeah, okay, instead of being over here at 1 and 0, we're at -1 and 0. Easy peasy. That would also make me think that if I picked a point over here of negative e, again, I'm just choosing the negative version of the original. If I pick a point at negative e, I should now probably get -1. That's what I think it'll be, just using transformations. So let's have a test again. Y equals negative ln of negative e, negative ln of positive e. Now, ln of e just cancels out. We know that cancels out. That ln of e is what we use to cancel out when we're trying to solve exponentials. So we know that's equal to 1. So -1. So yeah, that does check out. That's exactly what we thought it would be. So again, I've got my key features here, just using transformations to end up sketching this log. Now let's look back at all of these different examples here. They all have different transformations. We've got h transformation, we've got h and k, we've got a and b, we've got an A and B again. Okay, all the different transformations do different things. Okay, if you want to see an example where there's things like A and K, those sorts of combinations together, just let me know in the comments and I'll make you one of those examples too.